Welcome to this presentation on electric power. We're going to use the water pipe analogy just to get a bit of an understanding and appreciation about why the formula is correct, and we'll do some examples. So from a previous presentation we looked at a water tank providing pressure for water to flow through a pipe. The greater the water level, the more pressure it exerts on that pipe and allows a greater flow of water to go through, and the voltage was likened to that pressure and the current is likened to the water flow. Just rearranging that tank, and let's make a big dam, so a lot more water there, and here's a pipe network coming from near the top of the water up there, and water is flowing through this pipe. If I put a big paddle wheel on there, a turbine, then water can start flowing through that. And as some of you might already know, if I attach a big generator to that turbine, I can generate electricity. So ironically, I'm going to talk about electricity being generated from water and using water to be the analogy of electricity. So, the fact of electricity being generated is just this notion of electrical power, so getting power from water flow. If I start drawing electric power away from my turbine over here, I have to be taking energy from the water, so therefore I must be applying some resistance to the water flow. So water's flowing down this pipe, I'm taking energy away, so therefore I'm resisting the flow, decreasing the flow somewhat, and I can capitalize on that energy, that power, and take it away as electricity. If I maybe gear up my turbine so that I can run a higher speed generator, I must apply a greater resistance to the water flow. If I'm going to try to extract more energy, I have to be taking more energy away from that flow, so that means reducing the flow. Likewise, I can make it a bit easier, and the water will flow through a bit quicker, but I'm not taking as much of that energy away from the water. If we talk about power, we've already just talked about a few things here. So the amount of water flowing through here is going to be what enables us to extract that power. So the more water that flows through, the greater the power. The harder that water pushes, the greater the power. So I could raise the water level, as I just showed there. Raising the water level is increasing the pressure. So increasing the pressure, I'm pushing harder against the turbine. I'm able to turn a bigger turbine, for example, or turn a turbine faster, gear it up, I can extract more power. So more power comes from more pressure. Likewise, I could put a whole bunch of parallel networks of generators there, and I'm taking more water out and generating, in this case, twice the amount of power, because I got twice the amount of flow. I could, instead of having parallel arrangement there, maybe I could just make a bigger pipe there and have more water flowing through. So the greater the flow, the greater the power. So greater the pressure, greater the power, greater the flow, greater the power. Now power by definition is just energy per unit time. Its units are watts, so joules per second. Flow rate is a volume per unit time, meters cubed per second, and pressure is a Pascal, a Newton per square meter. Now, I'm just going to be a little bit clever over here, and I'm going to multiply my Newton by a meter, which means I have to multiply my bottom of my units over here by a meter as well, so length and length. A Newton meter is a joule. Now, the reason I'm doing this is just to show that it all works. So a Newton meter per meter cubed is a joule per meter cubed. So joules per meter cubed, flow rate meter squared. So pressure can be expressed in energy per unit volume, flow rate volume per second per unit time. And if I multiply my pressure by my flow rate, then I'm multiplying my energy per unit volume with my volume per unit time. Just rearranging those another way there. These units can cancel out, those quantities, so the volumes can cancel out, leaving me with just energy per unit time. And energy per unit time is the definition of power. So the watt, so joule per second of power. So power is equal to pressure times the flow rate. And our analogy is pressure is voltage, flow rate is current, so power is equal to voltage times the current. And in simple forms we have P equals VI, and just to show that unit analysis, that those basic concepts work, volt is a definition of a volt is a joule per coulomb, so how much energy is provided to unit charge, and the current is the charge per unit time. So those charges cancel out, leaving us with a joule per second, which is a watt. Right, let's get into an example, and here's an example using the actual water flow. A pump provides a pressure of 6 kilopascals to a device, and it results in 3 meters cubed per second of water flowing. What power is supplied to that device, or what power is provided by the pump? So just that recollection, that Pascal is can be expressed as a joule per meter cubed. So the pressure is 6K, so 6,000. Flow rate is 3, and all those units align with each other. They're all correct units. So power is just simply the pressure times the flow rate. Multiply those two together, giving us 18,000 watts, so 18 kilowatts. Example 2, now we want to be talking about electricity, so let's use electricity. So 6-volt battery runs a light for 10 seconds. If the light draws 600 milliamps, how much energy was used by the light? Okay, so the voltage is 6 volts. The current in milliamps, to keep it all correct, keep all those units working together, we've got to convert the milliamps to amps. 0.6 of an amp. Power by definition is voltage times the current, so 6 times 0.6 is 3.6 watts. And power is just energy per unit time. And we want to find out how much energy, so multiply the time across. Energy is power times time, 3.6 watts times the 10 seconds, giving us 36 joules. Another example, so John plugs several power tools into a power board, which is plugged into a 240 volt power board, and it has a 10 amp circuit breaker. So the circuit breaker is if I draw more than 10 amps, it just cuts out the electricity to that line. Can John simultaneously run a 1200 watt angle grinder, an 800 watt exhaust fan, and a 900 watt power drill at the same time? So these are all obviously drawing power parallelly. And we want to know, is the current going to be too big to allow that circuit to keep operating? So the total power, 1200 plus 800 plus 900, so we've got 2900 watts there. We know what the definition of power is, P equals VI, so let's rearrange that formula. The current is equal to power divided by the voltage. 2900 watts divided by the 240 volts supplied, giving us a current drawn from that power point of 12.08 amps. So that's too big, so we're expecting that circuit breaker to cut power off to that line. This is AC in home. Look, for all intents and purposes for this information here, it works the same as DC. Here is a circuit of that previous example, so that was a 240 volt supply. Again, AC, not quite that DC thing here. Here's our power board, maybe the switch there, so there is our 3 implements, and each one of those running in parallel. So let's do an example with this. So here's a 12 volt battery providing power to 3 components there, with a 5 ohm, 10 ohm and 20 ohm resistance. What is the total power provided by that battery? Okay, so that current all comes from that battery. It splits up into each of those. They're all parallel. I could easily work out, well, not easily, but fairly straightforwardly, I can work out the currents for each of those. We got voltage, we got current. We can work out individual powers, or we can do it all at once. So let's do it all at once. So we know our resistance for all parallel arrangement of resistors is 1 over R1 plus 1 over R2, and in this case a third resistor, so 1 over R3. Chuck in those values and solve for that. And remember, that's a definition of conductance. Take the inverse of that to get 2.86 of an ohm is the total combined resistance. I know that V equals IR, so what's the current coming out of that? I equals V over R, 12 volts over 2.86 of an ohm. is 4.2 amps. So 4.2 amps is leaving that battery. I know 12 volts, 4.2 amps, so therefore I know the power supplied by that. P equals VI, 12 times 4.2, we've got 50.3 watts. Let's go to another example. So similar as before, but now I'm saying, hey, what's this unknown over here? So 12 volts, and it's the same resistors, unknown resistor here. The battery shown loses 3,000 joules of energy in 1 minute. What must the resistance in R3 be? Okay, so power is energy over time. 3,000 joules over 60 seconds. That works out to be 50 watts. That's just that's very similar to that previous one. So we're expecting somewhere around that 30 ohms there. Sorry, about 20 ohms, not 30 ohms from the previous question. So from P equals VI, power is VO times I. Current is the power divided by the voltage. So I have 4.17 of an amp, so 50 watts divided by the 12 volts. 4.17 of an amp is leaving that battery. So that 4.17 amp is splitting up into this resistor, and then this resistor. So if I can work out the resistance coming out of these guys, then the rest of it must be going through this resistor. If I know if I know the current, I know the voltage. Therefore, from Ohm's law, I know the resistance. So the current, which is going through R1, is just the voltage times it divided by its resistance. So 12 over 5, 2.4 of an amp going through R1. Through R2 is 12 divided by 10, so 1.2 of an amp flowing through here. And as said before, the remainder of that 4.17 is flowing through R3. So 0.57 of an amp going through R3. I know the current, I know the voltage, so therefore I know what the resistance must be. So using Ohm's law, V equals IR, R is V over I. 12 divided by 0.57 of an amp is 21.1 ohms. So if you want to pause the video, here's a challenge. See if you can work out that value in a slightly different method. So work out that power as before, and we can work out the current. If we know what the power and the voltage and the current are, then I can work out what the equivalent total combined resistance must be, just using Ohm's law, and then using the parallel arrangement, we can equate that to that resistor and see if we can find out what R3 is. So pretty much it is the same method, it's just approaching it from a slightly different perspective. Let's see if we can solve that. Here's another final example. So here for this circuit here, 60 volts providing power to these three resistors, these two in series. How long will it take this resistor to use 500 joules worth of energy? So current is split up into this branch and this branch. I know the voltage across this. Let's work out the total resistance through here so I can work out the current going through this branch over here. So 30 ohms combined, a total through that little leg. From Ohm's law, I know that V equals IR, so I is V on R. So 60 divided by that 30 ohms gives us 2 amps flowing through that leg. So 2 amps is flowing through R1. From Ohm's law, V1 equals I1 times R1, so I know what the voltage drop from R1 must be. So 20 volts there, the remainder of that 60 must be 40 volts over here. And I know the power is voltage times the current. So I just worked out what the voltage must be, I know what the resistance is. Let's plug it into this formula over here. So 20 volts times the 2 amps which is flowing through it, so 40 watts. So this resistor is expelling 40 watts of it with power. Power is energy over time, so time is energy over power. So the time to use 500 joules using 40 watts per second is going to be 12.5 seconds. Okay, that's the end of our presentation.